Why hello friends, Jen Foxbot here for another edition of Math Mondays. Ba-na-na-na-na-na, yeah! Alright, we're gonna switch gears from algebra temporarily because this is my birthday week. So I wanted to talk about the birthday paradox, woohoo! The birthday paradox is not so much a paradox as a very weird and not intuitive outcome of probability. So basically, the birthday paradox question is, how many people do you need in a room to have at least a 50% chance of finding two folks with the same birthday? Turns out, you only need 23 people in a room to have a 50% chance. But remember, this is probability. So just like flipping a coin, it does not mean that every time we're in a room with 23 people, someone in that room is going to have the same birthday as someone else. It does mean that perhaps every other time you're in a room with 23 people, you'll find that to be true. But again, the more trials or more circumstances that we have, the more we'll find that 50% of the chance, or 50% of the time when we have 23 people in a room, that two folks will have the same birthday. One thing that I want to point out is that probability, especially when we're talking about things like birthdays, it's really helpful to remember to pull ourselves out of the spotlight, because it's not saying that those 22 other people might have the same birthday as me. It's just saying that out of those 23 people, that two of those folks will have the same birthday. It has nothing to do with me, which is probably a good thing. Okay. So to really understand this issue, it helps to build up an understanding of how we come up with equations to calculate probability. So I'm going to do two things in this video. The first is we're going to talk about comparisons, and we're going to use this simpler example to build up an equation that allows us to calculate comparisons between a large number of people. So we will build up the equation by doing small examples, and then we will do the exact same thing for the probability of finding two folks with the same birthday. So this might get a little long, but you can also break it into parts if you want. Okay, here we go. So let's say I am with one other person in a room, and I want to ask, how many comparisons can I make? And ask, do we have the same birthday? Well, with two people, we can only make one comparison. Oh. But with three people, how many comparisons can we make? Let's count them up. 1, 2, 3. Okay, so not too many comparisons. You ask your friend if they have the same birthday as you. You ask your other friend if they have the same birthday as you. And then your two friends get to ask each other. 3 comparisons. What about 4 folks? Let's count it again. And by all means, do this. Let's do this together. So if you have a piece of paper in front of you, go ahead and do the same thing. So we're going to count 1, 2, 3, 4, 5, 6. 6 comparisons. I feel like I'm in a Sesame Street episode. 6 comparisons. Okay. All right. What about 5 people? Okay, let's do this slowly so I don't miss any. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we got 10 comparisons. Sorry, I couldn't resist. Okay, now we have enough data or information to be able to write an equation that we can then use to make calculations for larger numbers of people. Because let's be real, this is way too time consuming, and this would turn into like a 64-hour-long video. So what we're going to do is we're going to say, we are asking, what is the number of comparisons that you can make between a given number of people? So the number of comparisons, or COMP for short, where n is the number of friends or people. They don't have to be friends, I suppose. Equals, okay, let's see if I can do this right. Okay, that is a really weird summation sign. But this symbol, that one's really pretty. That's a much better version. It helps that I'm not reaching and worried about sliding off the counter. So let me see if I can draw it a little better. So the number of comparisons equals the sum, starting at I equals 1. This is our index for each sum that we do here. I gets added by 1, or I increases by 1. And our ending state is when I equals n. So we are going to sum the term to the right starting at I equals 1 until I equals n. And what we are going to sum is the total number of people minus our index. So anytime your teacher says this is the case, you should always double check, because in math, that's what's so cool. When we understand something, we can double check and make sure that it makes sense. I'm going to erase this so I have some more space. And so you should double check this. And actually, let's do a little bit of that together. So let's test our case for 4. So let's say n equals 4. Then let's find the number of comparisons. We'll just say that for short. Equals, let's walk through this. So for our first case, so in this case, n is 4. So the first sum is n minus 1. So 4 minus 1. And then our summation tells us that we add a plus sign in between the next term. And the next term is 4 minus I equals 2. So 4 minus 2. And so in this case, I equals 1. In this case, I equals 2. And then we add 4 minus, we add 1 to I, and so that gives us 3. And 4 minus 4. So 4 minus 4 goes to 0, and we are left with 4 minus 1 is 3, plus 4 minus 2 is 2, plus 4 minus 3 is 1. 3 plus 2 plus 1 is 6. Huzzah! We got the right answer. That's good. Okay, but you're like, I still don't believe you. What is this shenanigans? Which is fair. So let's try it for n equals 5. So again, we start with comparisons equals 5 minus, our first case is I equals 1. So 5 minus 1 plus 5 minus 2 plus 5 minus 3 plus 5 minus 4. Okay, plus 5 minus 5. I wasn't going to write that because it's just 0, but we stop when I equals n, so I should probably be consistent. Okay, and so now 5 minus 4 is 4, plus 5 minus 2 is 3, plus 5 minus 3 is 2, plus 5 minus 4 is 1, plus 0. 4 plus 3 is 7, 2 plus 1 is 3, so we get 10. Yeah, that's exactly what we wanted. So we can go check this is a good equation for the information that we gathered by hand. And that's what's so powerful about mathematics, is that we can write equations to represent counting by hand. So now I can say, check this out. So what if n equals 23? What is c? Well, it would take you a long time to write that out, and I want to make sure that we get to the other part of this video. So double check this, break out your calculator. But what I got was that when you have n equals 23 and you plug it into this equation, you get 253 comparisons. What? That is wild. When you have 23 people in a room, you have 253 times that you can ask the question, do you have the same birthday as me? That's a lot. And so if you think about it, when there's 365 days out of the year, if you have asked, do you have the same birthday as me, 253 times, that's a lot of times. And okay, so you can make an inference like, okay, we're starting to get up into this it might seem likely that 2 people in a room of 23 would have the same birthday. Cool. But we still haven't talked about probability yet. So let us break into that.